Hello learners, hello grade 12s, welcome to Edge Blush Virtual Academy. We are still looking at our very interesting topic, which is work energy and power. And we are now on lesson number 6 under that topic. And we are still looking at the application of the work energy theorem. Now, in our previous lesson, we were looking at the work energy theorem of with a horizontal crate that has been pulled to the right by force applied. Now I'm going to look at an incline whereby a crate or a block is falling on an incline of 20 degrees to the horizontal. So I'm going to draw the diagram and then we try and answer the questions that follows using our work energy theorem. So the question that we have, it's an incline. I'm going to draw the incline here, and that is our incline, which is 20 degrees, right? And then we have that point, which is point B, and we have that point, which is point A. Then we have our block, which is the block is 70 kg, right? And this is our displacement, which is 12 meters, like that. So this is point A, that's point B, and as the block is sliding down, it is experiencing constant frictional force of 190 newtons, right? So question A, it says draw free body diagram. That's A. Draw a free body diagram, right? Draw a free body diagram and 3 marks. Number B, calculate, right? Calculate net work done. Calculate net work done on the crate. Net work done on the crate during its motion. During its motion from point A to B, and it's 5 marks. Then item number C, it says use the work energy theorem. Use the work energy theorem. Use the work energy theorem, right, to calculate. Use the work energy theorem to calculate the speed of the crate at point B, right, at point B. If it passes point A, moving at 2 meters per second, and it's 4 marks. All right, so we are presented here with an incline. We have got an incline, and we've got a crate or a block of 70 kilograms, which is sliding down on its own. There is no force applied there, right? And as it passes point A, we are told that it was moving at 2 meters per second, and it is experiencing a constant frictional force of 190 newtons, and this is kinetic friction because the object is in motion. So that is what we have. The incline is 20 degrees from the horizontal. So item A, okay, it says draw a free body diagram. Now, normally, when we have got 3 marks, normally the number of marks, they correspond with the number of forces. So I'm going to draw the free body diagram. I put a dot to represent the crate. So I've got my friction, which opposes motion, and I've got my Fn, which is perpendicular to the surface, and then my downward force, which is Fg, or the weight of the object. So that is the free body diagram. Now, when they request you to draw a free body diagram, we don't put components. We draw the original vectors, the original forces acting on the object. We might need the second free body diagram where we resolve Fg into components when we do our calculation. So that is the free body diagram, and you get your 3 marks for that. Remember that friction always opposes motion. If the object is going down, then friction must be going up. And your Fn is always perpendicular to the surface, and Fg is always downward. Then let's move on to item number B. Calculate the net work done on the crate during its motion from point A to point B. So we have got 3 options for calculating net work done. We can calculate work done by each force, or we can use W net is equals to F net, or we can use the work energy theorem. Now, when you look at the context of the whole question, we can't use the work energy theorem on question number B because we are yet to calculate the speed at point B. So work energy theorem is out. Now we are left with the first 2 options. We can calculate work done by Fg and then work done by friction. We add the 2. Or we can use the F net. Now, if I am to use the F net, I have to resolve my Fg into its components so that it becomes easy for me to get the F net. Like I said previously, I've got a bias towards the second option, which is the F net method. So that's the one that I'm going to use here. So W net is equals to F net by displacement by cos theta. Right. I have to resolve my Fg into components. So I'm going to come up with another free body diagram. So can I draw it here? So the second free body diagram that I'm going to get, I'm going to have my Fk, then my Fn, then I resolve Fg into components. I will have Fg parallel and I will have Fg perpendicular. Now, when you look at this free body diagram, Fn and Fg perpendicular, they do no work because they are both perpendicular. So the forces which are acting actively on the crate or a block is Fk and Fg parallel. Allow me to take the direction of motion as positive, which is down. So throughout my calculation, down is positive. So it means my F net is equals to Fg parallel plus minus Fk, because Fk is opposing motion, it's going up, so it's negative, right? So W net is equals to my F net is going to be adding the forces that are parallel to motion, which is Fg parallel and Fk. But direction matters, so downward we said is positive, so Fg parallel is positive. So W net is equals to Fg parallel minus Fk, right, times displacement times cos theta. But we know from our previous calculations, friends, that Fg parallel is mg sine theta. So we can as well calculate it separately. Fg parallel is mg sine theta. And when we calculate Fg parallel, your sine theta, your theta is the angle of the incline. So Fg parallel is equals to, the mass is 70, g is gravitational acceleration, which is 9,8, which is sine multiplied by sine 20. So Fg parallel alone is equivalent to sine 20, you close there, times 9,8 times 70. you get 234,63. This is our FG parallel only. So we need to substitute that in our formula. So W net is equals to 234,63 minus our friction, which is 190. It's given. Multiply by displacement is 12 times cos. Our theta, we are getting a positive F net here, which means direction of F net is down and the object is going down. And remember, under cos theta, your theta is the angle between force and direction of motion. So your F net is positive, which means it's going in the downward direction and the object is going down. So your theta is going to be 0 degrees. So your W net is equals to, so 234,63 minus 190, you get 44,62 times 12, right? Times cos 0, you get 535,51 joules. This is your network done. So you realize that even if you use the other option, the other method, which says net work done is equals to work done by Fk plus work done by Fg, you will still get the same answer, which is 535,51 joules. And remember, if you decide to write your answer decimal, it has to be rounded off to 2 decimal place. So that is our answer for item number P. So it means as the block moved from point A to point B, the network done is equivalent to 535,51 joules. Then item number C, I'm going to calculate it on the other side. Use the work energy theorem. You see, when the question or the examiner is so specific, so particular about the method that must be used, we are now guided. So we are not at liberty to use any formula that we want. We definitely have to use the work energy theorem and nothing else. So item number C, we cannot talk about it because it's already guided. So use the work energy theorem to calculate the speed of the crate at point B if it passes point A moving at 2 meters per second. So we are using the work energy theorem, which says W net is equals to delta EK. Remember, there is a mark for writing the formula as it is. So just writing that formula and trying or attempt to substitute, there is a free mark for that. So our network done we've already calculated, which is 535,51, which is equals to, how do we calculate change in kinetic energy? It's half mv squared F minus half mv squared I. So it's going to be half times mass 70 times final velocity is what we are looking for at point B, minus half times 7 times 70, which is the mass, times what was the initial velocity, what was the velocity at point A? They said it's 2, and we don't forget to square. So 535,51 is equals to 35 VF squared minus, okay, I'm getting 35 times 4. That should be 1/4. So we collect like terms there. So we are going to have 35 VF squared is equals to, we take 1/4 to the other side. It becomes positive, right? So it becomes 1/4 plus 535,51, and I'm getting 675,51. Divide both sides by 35. Divide both sides by 35. So VF squared is equals to this one divided by 35. I'm getting 19,30 square root square root. Therefore, VF is equals to Square root of 19,3 is 4,39 meters per second. So that is the speed of the block at point B. So the crate passed point A moving at 2 meters per second, traveled a distance of 12 meters, and by the time it passes point B, it was now moving at 4,39 meters per second. Since it's downwards because of gravity, it makes much more sense to me that it has actually gained or it has increased in its speed because it's going down. It means the friction is not big enough to slow or to stop the block. So that is the work energy theorem. That's how we apply the work energy theorem in our calculations. Let us be very diligent and let us be very sensitive with the use of terms. Right. And I want to repeat what I said earlier on. I said if they say the object was moving at a constant speed, then it means your delta EK is going to be zero. So in other words, your formula is going to be W net is equals to delta EK, then W net is equals to zero because there is no change in kinetic energy if the object is moving at a constant what? At a constant speed. So that's it, friends, grade 12s. So in my next presentation, which is going to be lesson number 7, I'm going to deal with mechanical energy and the law of conservation of mechanical energy. Thank you so much for watching Edge Blush. We love you all.